Okay, so we will prove this Park-Pham theorem. But in order to make some calculation easier, we slightly change this theorem. So here, what you randomly choose this subset in a way that each vertex is included with probability p, independently at random. But instead, we imagine that we are choosing a set of specific size at random. So this is a bit different, but the difference is not big. Here is the constant, say, C, satisfying the following. So this is what we were going to prove. So let's say your H is an L-bounded hypergraph. The MBH size and motor on the vertex at X. And it is not P-small. So it does not have a good cover, P-small cover. Okay. Of course, here. And what you know is that if you choose a uniform random set of size like P times X times log L times large constant subset. So out of all subsets of this size, you choose one uniformly random. And that belongs to, this. The hypergraph, which is generated by the, elements here. This is increasing property. This is arbitrary, like, yeah, I made some mistake. Make type of an minimal set in F. So this is the maximum size of a minimal set in F. And here, this corresponds to the increasing F. Then which is like if corresponding to the correlation of all minimal edges in a minimal set. Yeah. So this is our increasing property, and then this is the correlation of all minimal sets. And it belongs to this, meaning that it is contained an element in H with high probability 1 minus 0. So this tends to 0 as L increased, L goes to infinity. Okay, this is what we want to prove. Okay. Now what? Let's say that your set X is size N. And let L be a large constant. Now what? For each I, we let Li be 0.9 I times L. Technically, you have to take like ceiling or floor to make it integer. But we will not put ceilings and floor and treat them as like their integer. And let K be a minimum integer. Such that if Lk becomes smaller than 1. And what we know that K is something like almost 100 times lower. This we know. And we define Li, which is either L or L times square root of log L, if like I is not too big, and if I is close to this K. If I is between 1 and K minus square root of K, then this is L, otherwise it is bigger. And for the first case, what do we know? We know that Li, which is like 0.9, at least 0.9 to the K minus square root of K times L is like, we know that the K is roughly constant times log L. From there, this, you know that this is like, okay, maybe. So we can easily check that this is at least e to the, say, K minus I over 100. And by applying this, you know that this is at least like e to the like 1 over 100 root of log I. Point is that for first case, if Li is not too much. And now what we do? We let x0 be as x, and h0 is your original hyperbolic h. So you have your that x, and there you have like many edges. Hyperbolic. And what? Now, for each I, what we will do? We choose a set Wi in which is subset of x of I minus 1, and which has size exactly Wi. We choose it uniformly at random, where this Wi is exactly Li times Pn, and we will let xi be the xi minus 1, and we delete this. So somehow what? We choose the W1. And now in here, if it's x1, and in here, you choose a W2. Now here, this is x2, and you choose W3, and so on. That's what we will do. And while you're doing that, we will also update this hypergraph. And in the end, what? In the end, we obtain random set of size if it's a union of it or some constant C. So why it's you define it this way, right? And what Li is I for this many. So every time you choose the same set of same size up to I minus K minus square root of K, and K minus square root of K roughly like log L. So this gives us the P times log L times N times some constant set. And later, when here, again, like you take a set of this size, or square root of L many, and square root of L, again, square root of K is again square root of log L. So you collect them, again, that's like some constant times log L times Pn. So in the end, I mean, you have this many, I mean, some set of this. Then we will show that with high probability, some point, I mean, is that covered at least one of these edges with high probability. That's what we want to show. So we aim to show that this W entirely cover at least one edge of H. And what? Let's say you have this S which is in here, and say that the W1 is here and W2 is here. And after that, this part is already covered. So these are left to be covered. Okay. But if we know that there is like another S prime, which may look say this way, S prime, and as long as we just consider the uncovered part, S uncovered part is here, and S prime uncovered part here, and S prime uncovered part is smaller. Right? In this case, what? We don't need to consider F anymore, but to more focus on this S prime. Why? Covering S prime is easier. If we actually cover entire S later by say W3, W4 at some point, and we automatically cover S prime, so we don't really need to consider about S anymore. So S prime is more things to focus. This motivates the following definition. Given the F and W, arbitrary set W. Okay, so W is the defined as, let's say, W star. And this is some arbitrary set that we and a hypergraph, the H I minus 1, we say that T, which is determined by F and W, is we say minimum SW fragment if T is the set of smallest size, such that if T is S prime minus W or some S prime in this hypergraph with this. So instead of this S, you consider this S prime. What happened? This S prime is the subset of here. So uncovered part is subset of uncovered part of X. Out of all these choices, you choose the one that this uncovered part is smallest. So this is the smallest one. And you say that this is the minimum SW fragment. Okay, then what? Now, while you're doing this repetition, now we keep track of the hypergraph. So for given hypergraph, Hi minus 1, we partition the edges into two ways. One is H prime I, which is you consider all the edges whose minimum fragment Wi is chosen, right? And according to this Wi, you consider Swi minimum fragment. And then if that's more, then you put the edges in H prime I. And Hi is the ones you only consider the fragment where the if S is in here. So what I mean is that, okay, as I mentioned, we only need to consider this S prime, right? And then this part is already covered. And in your new graph, you might treat as this is your edge. You don't even have to consider this anymore because that's a superset of your edge here. So you just collect it. And then you just put it in your next hypergraph. And then you choose W3 and then hoping that the W3 covers it. As long as W3 covers one edge there, then it covers it together with W1 and W2. It covers everything. I mean, everything in one edge. So we only have to consider this T in your next iteration. Because W1 to Wi minus 1 are like already, I mean, Wi, up to Wi, you already have considered. And then the covered part you forget. And then in the remaining, our aim is to cover it. So this is your next. But we only consider the one that's substantially shrink. If this is substantially shrink, then you put it here. And you pass it to the next graph. Otherwise, you will not pass it if this minimum fragment is not substantially shrink, and we will actually cover it. We will find the cover for it. So this minimum fragment is small here, but the remaining edges they are not more. So they kind of, I mean, ensure that they can be effectively hammered by the following cover. But let's consider this early UI as you consider all the minimum fragments or all the edges not passing to the next one. So that now defines how this hypergraph evolves over the repetition. So we repeat this for all I from 1 to k. And from definition, what we know is UI on the cover, because what? Then here, for each S, you take this minimum fragment. That means this from the cover of this. So this is a cover of like sorry, so here I is yeah, we put the time on the other way or you know if and also if we find the cover of H say I, then it is a cover of H I prime. So if you have a cover for this, it means that the JIT cover contains a subset of, I mean, for every set here, you can find the subset here. That means it's covered. And that naturally provides that this is also a subset of something here. So that means that provides a cover. So for each F, so there is a subset of S here. Then this has a subset in this cover. So any cover of HI is cover of H prime I. So that means that if you find the cover of HI, then that's cover of H prime I, which was not covered before. Then if you take this cover and then this cover, then that covers everything here. So that means that yeah. So you just collect them, then that's gonna cover all the previous one. Edges that's not the right. The edges that we did not keep too far is all covered by the union of UI. You take U1, U2, U3, U0, U1, U2, U3. No, U1, U2, U3, then you take the union, then that's covered for all the things that we have not kept yet. And with that, we know the following. Either W is in cover, I mean, W contains our W star, and then the set that we choose, we can show that either this one, if in here, meaning that it contains an edge of H, or our U, which is the union of UI from I1 to K, covers this H. So one of them happens. Why? What do we know? So every time what? We kept the ones which is size 0.9 Li, Li minus 1 here. So Li minus 1, this is Li, right? So here, and then you take this. So everything here has size at most Li. So this one is smaller than that. So this definition ensures that the next time your hyperedge is Li bounded. And then it keeps down. And at that point, after case time, you have a hypergraph, which is Li bounded. That means edges there do not have any size, at least one. And we have two cases. We either have that the HK does not contain any edge, or it may contain an edge which is empty. So this is the only possible scenario. In the former case, it's empty, means that every edge will be kicked out. Every edge is covered by this cover. That means that and like the bore some edge space F in here, and see how if how it corresponds to edges, the F0, which is that, and F1, F2, dot, 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 in its H0, H1, dot. In this iteration, you know that either it is covered by UI in this iteration. We know that either it is covered by our UI, or it survives to the next one. But this contains no edge means that every edge is covered at some point. As if it's empty, every edge is covered at some iteration. Hence, this edge is covered by you every H is covered by no, the letter. And other case, if this HK contains one H which is empty set, that means empty set is the TS I minus 1 WI or some I here equal some S in S. And what? This implies that this minimum fragment is empty, means that W1 to WI contains an H of H, hence this W is in this increasing property generated by the hypergraph. So W contains an H. So this claim holds. So now let's give a name to this event epsilon. Is the event that this U covers H. Okay? Then by the above claim, what do we know? The probability that the W contains an H of H is at least 1 minus the probability of the event. Because one of them must happen, right? And what do we know? We know, they recall that this H is not P small. So, I mean, if this epsilon occurs, and this U provides a covering, that means if you take all elements in this cover and then you add the P to the size of U, then that's bigger than half. Okay, from this, what do you know? Probability of this epsilon is at most like because of this. So if this occurs, then this holds. So this is the most the probability that our choice of this cover have a measure bigger than half. So remember this U and everything is random variable. So you can actually compute the probability that this one has a specific value. So our random process give you this U, and then for that you can compute this. Then you have this inequality. And what? By Markov inequality, what? This is twice times the expectation of this number. Okay, so now it suffices to show that this one is small. You can write it this way. On each AI, you consider like this is below 1. So if this one is little 1, then this one is little 1, and this one is 1 minus little 1. So it's going to be our conclusion. Okay, so now we just compute this. With that, we claim that the following. For each I, its expectation for fixed I is at most L to the negative 0.8 Li. Technically, Li. For each I, you have a different value of I. Let's say your ni minus 1 is the size of xi minus 1. I mean, it's roughly n, but you have scooped out some parts like wi, so you may have a slightly smaller value. But it's essentially n. And let's say you consider this, let's give a name that A is the expectation of this. And that's like what? Out of all these choice, so that's your choice of wi. And you consider all of these choices. And for each choice, you consider what you would get here. And then you add them all together and then divide by this. Where this UW is the cover we obtain if your WI happens to be exactly this. And let HI prime W and HI W be the hypergraph. H prime I and HI we obtain if WI again happens to be your W. And now you can compute this A. How? So depending on, I mean, what power you have to take. If U, let's consider that, let's say that's M, then it's between, so let's subtract L sub I. Remember that what do we cover? So in here, remember, if it is small, then you take the minimum fragment and then you pass it to the next one. But in your cover, the ones that you consider are the pets whose minimum cover is not so small. And then you take the minimum cover there to get your cover. Minimum fragment is what you take. And there, the minimum fragment size is between 0.9. It's bigger than 0.9 Li minus 1, which is here, and then at most L sub I minus. And each of them, you take P to the M, but how many choices? You consider all the minimum fragment. And this W is the all possible set, and S is all edges that survived. And then let's say your minimum fragment has exactly size M. So you count such cases. You count all such cases and you add. And you have to also multiply. And I minus 1 choose WI together. So here, you consider all W, and then you consider all U, and then here. U in this cover is actually T, W, TSW for certain choice of X and P. So this summation, you can consider it as like you first fix the side or possible side, and then you count all the possible choices of W, and then if U minimum fragment. So this is same, yeah, and you have to divide by this. Okay, now you want to estimate it. How do we estimate? We first fix M and we consider all possible like n of I minus 1 choose Wi plus M choices. So that's a G of size exactly Wi plus. And if this G contains an edge of your Hi minus 1, then we make one arbitrary as G, which is the net here. Okay, then this G will play the role of W union T. So what? For each such G, we count the tuple W, TSW that satisfies that G is the W union with T is exactly, and where this T is the TSW. And what do we know? So, I mean, how we define this minimum fragment means that you have like this W and T. T is defined as is a minimum fragment of some S, means that there are like some F here, and then F prime, which is actually lies within W prime, W union with T. That means if this count is non-zero, if this count is 0, then yeah, we don't have to count anything. Non-zero, then SG is defined because there are at least one set here which is contained in this union. So out of them, we made some arbitrary choice. Moreover, what we know is that we have that this P is subset of SG. Why? And otherwise, I mean SG, because SG is the subset of G, right? And yeah, subset of W union T. Right? If this does not contain T, that means its intersection here, it's missing some vertex here, and SG minus W is a set smaller than T, which is contradiction of the definition of the minimum fragment. And this is a smaller set, and T minus W, contradiction of the definition of minimum fragment. Thus, what do we know? For this G, we have a SG. Then what I just said above holds for any such choice. It means for given G and SG, the number of possibilities for T is at most what? 2 to the Li minus 1. Because it's subset of that, and then it has guide at most Li minus 1. I mean, you can write it as a 2 to the ft isoft. And each possibility determines w as g minus t. So what do you know? If A is like this times, let's just copy what I wrote before. Is can be rewritten as the following. So m is between this and this, and then p to the m is still there. And then instead of choosing this, what? You choose all possible choices of G. And then in G, you have a FG. And then in FG, you take a subset T. And that T is chosen 2 to the L way. Okay, but what we know is that if Ni minus 1 choose Wi plus M, it's like locally Ni minus 1 times what's this? This is LT N plus M. So, and Ni minus 1 is like locally N. So ratio between these two is like LP. And then if you consider this and Ni minus 1 Wi, and then you compare these two, you just expand by using the formula for this binomial coefficient. And you will see that this is most like L times P to the negative M times Ni choose Wi. And this one becomes like L to the negative M and Ni minus 1 choose Wi 2 to the L. And this multiplication is everywhere. Like you that cancels this out. So this is the most like yeah, this is what it is. And overall, I mean you just like make the calculation. Yeah. You can say that this is like almost this. So each one of them will have to be equal to Li. Because the last is because L is sufficiently larger than 2. Okay, so this proves the claim. Now we have this claim, then you can compute this. What's this? So this can be prolonged by you divide two cases. So if I is small, this is of L to the 0. Negative 0.8 error. And here you have this. But the first case, it's largest when I is the smallest. So it's like you take root of log L. Something like this. And for the later part, what you take I, and each one of these is like L square root of log L, then up until to I is K, so this Li is bigger than like 0.9. LK is the first one that it becomes like one, smaller than 1, but so we can actually show that this one is more. Overall, everything is 0. So that confirms that I mean, this is small, so that this one is at least 1 minus 0 1. That proves what we want. So this trick of finding minimum fragment was main idea for this proof, and that kind of was originally suggested in an improvement of the sunflower conjecture, something called sunflower conjecture. And yeah, due to this like simple and creative idea, this theorem was proved. Okay, then that would be it for this course. And thank you very much for taking this course, and then we can take next. Thank you very much.